Hello friends, I welcome you all to my channel on fluid mechanics. Uh, so let us start studying something about fluid mechanics. At the outset, I would like to tell you that the definition of fluid comes from a difference, that is the distinction of fluid from that of a solid. In case of a solid, if this is the one, if you apply a shear, what will happen? For a particular type of shear force, you will be having a definite amount of deformation. So, a fixed deformation is there for a particular type of load or shear. Whereas, in case of fluid, if let us say that you have a river, this is the base of it and the fluid is this, or any fluid, and you apply a shear, what will happen? The fluid layers will move continuously, and if you can see that there is a continuous deformation state of this particular fluid. That simply means that in fluids the basic criteria is continuous deformation. So, continuous deformation is the inherent characteristic of a fluid. So, fluid is that substance that deforms continuously, whereas solid, for a particular type of force, you have a definite fixed amount of deformation. So, from here you can take two important points. These are that solids cannot they can resist the shear force uh, with a finite amount of deformation under static equilibrium condition, and they can regain that particular deformation partially or totally depending on the extent of loading you have applied, whereas fluid doesn't do so. Fluid can not resist they cannot resist the tangential force under dynamic condition, static condition. They will resist it only under dynamic condition, and once this is done, they will never ever come back to its original state. There are exceptions to it, but ideally speaking, fluid will never come back to its original state. That means it don't have that memory to come back. That's why some people also call that fluid is a zero memory substance. So, in solid mechanics, you have seen that there is a law called as Hooke's law, which relates the uh, shear stress to that of shear strain, and that relation is a direct relation between stress and strain, and this is what the constitutive relationship in case of solid mechanics is. But this relation is not valid in case of fluid mechanics. Why? Because in fluid mechanics, for a definite amount of shear force or stress there, you don't have a definite amount of strain. That means deformation. The deformation is continuous. So, to arrive at that particular constitutive relation, you should do what? You should take the average of the strain or deformation which is there, and that to a time average deformation or strain. So, before applying any Newton's law, we should understand that we are working in a continuum domain. That means the properties whatsoever are there, they are a continuous function of space and time. And these properties are valid throughout the domain. There should not be any spot left. To understand this, consider a fluid volume V In that fluid volume, consider a point P. Surrounding that point, you have, let us say, a small volume del V. Now, in this small volume del V, you have a mass del M, and when you divide with this volume, you will be getting density. And if you plot this with the volume itself and you shrink this volume to a lower value, you will be able to see till certain point you are not getting any disturbance. That means density is more or less a constant. But after this point, you will be getting a sudden drop either or a sudden shoot in the density. This is because after this particular volume, means if you reduce the volume further beyond this, what will happen? The dimensions of that particular domain would have been reduced to such an extent that if any molecules leave the domain, that will reduce the density, and if any enters, that will increase. If any enters, sorry, that will increase the density. So what is the point? The point is that we should always work in this continuum domain. So my working will be from here only. And to make this certain that we are working in continuum domain, there is a number known as Knudsen number, KNSEN, Knudsen number. Some people call it as K suffix n, which is nothing but the mean free path of molecules, that is the statistical average distance the molecules travel between two successive collisions, to that of the characteristic dimension or the domain, length of domain, whatsoever it is. If this number is less than point, if this number, I'm sorry, if this number is less than 0.01, then only this will be considered as a continuum domain. That means the characteristic dimension or the domain in which we are working should be much higher than the mean free path of molecules. And if this number, there are other distinctions as well. If this number is more than 0.01 but less than 0.1, this is considered as slip flow. If this number is more than 0.1 but less than 10, then this is a transition from slip flow to free molecular flow. So this is a transition from slip to free molecular flow. And if this Knudsen number becomes more than 10, then this is free molecular flow. So the thing is that we should always work in a continuum domain. Now, in fluid, whenever we try to understand fluid, we should understand it with the help of its properties. So some of the properties are viscosity, compressibility, and so on. So let us focus on this property called as viscosity. Before I talk of this term viscosity, the thing which you should understand is that viscosity only comes into picture whenever there is a fluid motion. If fluid doesn't move, then there's no point in talking of viscosity. Viscosity is sort of resistance offered by the fluid against its flow. So whenever there is a flow, then only we will be talking of viscosity, otherwise not. So viscosity means you are talking of flow. If flow is there, then only you will be talking of viscosity, otherwise not. So to understand how this viscosity or this viscous interaction come into play, you consider that, okay, let us say that this is your x-axis and this is your y-axis, and fluid is there. This is the free surface of fluid, let us say. Then this is a typical one dimensional, this is a typical, I must go back now. So this is a typical one-dimensional profile. That means I am assuming that velocity variation in this domain is a function of y only. That means if I move certain distance apart, I will not be getting any distinction in the velocity variation. It will remain the same. It will remain the same like this. So this is a example of this is example of one dimensional flow, and as the velocities are in one direction, so this is a one dimensional parallel flow. So if at any distance y you look very closely, then you will be able to find that there exists a shear stress field. So how that is happening, let us focus on a very small region of fluid here, and let us try to exaggerate the picture. So if you exaggerate this, you will be able to find two fluid layers like this. There are n numbers, so we have squeezed so that we are able to see these two layers, and we are magnified it. As you can see from the profile that as you move up in the y direction, so this is the layer at a distance y, and this is a layer at a distance del y apart from the layer beneath. This bottom layer is moving with a velocity, let us say u. Then this top layer will be moving with a larger velocity. As they are very close, so let us say a very small but large velocity del u. So what will happen? This top layer, as it is moving with higher velocity in comparison to bottom layer, so what it will do, it will try to drag or pull the bottom layer with it in this direction. Whereas as the bottom layer is moving with the lower velocity, so what will it do? It will, due to Newton's second law, it will try to oppose the motion of the first layer, as these two layers are interconnected. How? I will be talking this in very short while. So a sort of shear force comes into play, and due to this we can say that a shear stress field is also generated in the flow because of the variation in the velocity in the y direction. So we can say a shear field is there which can be represented as a function of y. So how this constitutive relationship comes into play? So to understand this, why not consider a fluid element like this and exaggerate this? If we consider this fluid element and exaggerate this, with respect to the bottom layer, the top layer will be moving with a velocity of u plus del u minus u, that is del u. So this is moving with a velocity del u. So the top layer is moving with a velocity del u in comparison to the bottom layer. So if you focus your attention on this particular point, so in a very small time del t, in a very small time del t, this point would have been moved to a distance this, and the distance traveled by this point will be del u times del t, and this distance is del y. So the deformation which is created, the same thing will happen here. So the deformation which is being created, let us say it is del theta. So if you write from the geometry, tan del theta will be del u del t divided by del y. For a very small angle del theta, tan del theta will be equal to del theta only. So this will be del theta is equal to del u del t by del y. You bring del t onto the left side, this becomes del u by del y. And in a limit when we just allow this particular point to move, that is in a limit when del t is tending to 0, what will happen? This becomes d theta by dt, and this becomes du by dt. So this is what? This is the rate at which the strain is changing with respect to time, or sometimes this is also called as rate of shear strain or shear strain rate, whatsoever it is. So the rate of shear strain is what equal to the velocity gradient. So what I'll say here is that the velocity gradient is nothing but the rate of shear strain. So Newton was the first to write that the shear stress in case of fluid is proportional not to the shear strain but rate of that. So that is d theta by dt. And here in this particular case it is du by dt. Therefore, tau is proportional to this velocity gradient, and this velocity gradient will now be called as rate of shear strain. So once you remove the proportionality, you will be able to write this thing as S, and mu is a proportionality constant and known as the coefficient of dynamic viscosity, which is represented as tau by du by dt. So this is coefficient of dynamic viscosity. This coefficient of dynamic viscosity is having a unit of, this is Newton per meter square, this is meter per second, this is second, so it is Newton second per meter square. This is dynamic because this is coming into play when the fluid is in motion, and you can very well see Newton term is there, so it is representing some sort of dynamic nature. And this is what tells you about the resistance offered by the material. And in this particular case, this particular fluid, as you can see, this is a linear relationship. So this constitutive relation is known after Newton, that is the fluid which follows this particular relation will be called as Newtonian fluid. So as in case of solid mechanics, we always draw stress strain curve. We can always do this for fluid mechanics as well, but with a slight difference that in case of strain we will be writing strain rate. And for these classes of fluid, Newtonian fluid, this is a straight line, and this slope is nothing but which is telling you about the dynamic viscosity. Apart from Newtonian fluids, there are other fluids as well which are called as non-Newtonian. Why? Because they doesn't follow this constitutive relationship, linear constitutive relationship after Newton. That is, shear stress is not proportional to shear strain rate. Direct relation is not there, so that's why they are called as non-Newtonian fluids. These non-Newtonian fluids are further classified into two. What are those? First one is time dependent. Another one is time independent. The time dependent non-Newtonian fluids are those where the shear stress and rate of shear strain relationship that changes with respect to time. The constitutive relationship, it changes with respect to time, whereas in independent case it doesn't change with respect to time. So the classes of fluid which fall under this category are your dilatant fluid, the pseudoplastic, the Bingham plastic. These are the classes of fluid which falls under the category of time independent. The constitutive relationship for these non-Newtonian fluids was given by a power law model by the name Ostwald-de-Waele model. This is called as Ostwald-de-Waele equation or model. This power law model is tau is equal to m du by dy n, where n is the flow consistency index and m is the flow behavior index. And in case of dilatant fluid, this flow consistency index is more than 1, whereas in case of pseudo, this is less than 1. So some people also try to write this thing in terms of viscosity. So what they do is they write this equation like this. So this becomes the definition of viscosity for non-Newtonian fluid. But remember, for non-Newtonian fluid, this is not a property. And this viscosity is no more called as viscosity. Instead, this is called as uh, this is called as uh, apparent viscosity. It looks like this, but this is not the one. This is not the definition of viscosity, because viscosity, dynamic viscosity definition, which you have seen earlier, that is tau by del u by del y, is the property of only Newtonian fluid, not for others. Remember this. So, if you draw these here, then this is your dilatant fluid. That means with the application or with the increase in the strain rate, the amount of resistance offered by the material increases tremendously. And the best example is your cornstarch, quicksand. Whereas in pseudoplastic, this is a sort of shear thinning fluid where the resistance reduces with increase in the strain rate. There is there are other fluid like this particular horizontal line represents an ideal fluid, means fluid which doesn't offer any resistance. Viscosity is 0 for this particular type of fluid. Though ideal fluid doesn't exist, but this hypothetical theory will help us to understand some of the properties of fluid which, or some of the fluid far away from the wall, as they shows this type of behavior. Whereas this vertical line represents ideal rigid fluid, or in fact not fluid. If it is rigid, it is ideal rigid solid. When we talk of Bingham plastic, that is ideal Bingham plastic, let us say, some of the researchers don't consider this in a class of fluid, because fluids are one that doesn't resist any shear. They don't resist any shear in static condition. The moment shear comes, they will start deforming. Whereas this type of fluid shows what? This fluid will only start deforming once you apply a yield. Yielding is required for these fluid. Example is your tomato ketchup and your toothpaste. So if yielding is required, then you cannot consider this as a fluid, because uh, the fluid for which yielding is required, they violate the basic definition of fluid. That means uh, that the fluid will not resist the shear in static condition. They will start deforming instantaneously the moment shear is coming into play. So that's why every fluid is starting from the point 0, and here yielding is required. So some people don't consider this Bingham plastic as fluid. So in previous case, we have seen that I have started the line, or I have started drawing the velocity profile from the base, that means from this surface, with a 0 mark. Why this? This is one of the fundamental boundary conditions known as no slip boundary condition. That means if this is the solid surface and the fluid arrives potentially, that means no variation in velocity is there, like this. Then the moment fluid comes onto the surface of solid, the it will instantaneously be retarded to the velocity of solid surface itself. That means the velocity of the fluid at the solid surface relative to this surface is 0. That means the fluid can never ever slip past a surface of a solid. It will always be be um, arriving at the velocity of solid. Don't consider this as the case of surface tension. No, this doesn't has anything to do with surface tension. This is because of the immense, large, huge frictional interaction between the fluid and the solid at the solid surface. So these velocities will be retarded because of frictional interaction within the layer and ultimately huge frictional interaction with the solid. So what will happen? Sort of this will be there. That means zero velocity at the surface. And if the surface at all moves with certain velocity, so the velocity of the fluid at that particular solid surface will be velocity of solid only. Therefore, this is what we called as the no slip boundary condition. So the velocity from very high value will be brought down to a very lower value due to the frictional viscous interaction between the layers of fluid, and at the same time due to a very strong frictional force between the fluid and the solid at the solid surface, which will bring down the relative velocity to zero value. So friends, in today's class, till this point only, I hope you must have enjoyed the lecture, and if you liked it, then please do subscribe it and share it with your friends so that others can also be benefited out of it. Thank you very much.